The Moon is the Earth's only natural satellite and its closest neighbor in space. According to the most widely accepted theory, the Moon formed after a Mars-sized body collided with the young Earth. This catastrophe, which occurred billions of years ago, melted our planet and ejected a huge amount of material into space. That material eventually cooled, took on a rounded shape, and became the Moon. Today, this crater-covered sphere orbits the Earth, causing ocean tides. Its diameter is just over 1/4 that of Earth's, making the Moon the fifth largest natural satellite in the solar system. The Moon has several phases: new moon, full moon, crescent, first quarter, and last quarter. But regardless of its phase, it is difficult to mistake it for any other object in the night, and sometimes even daytime, sky. Imagine waking up at night and noticing that the Moon looks different, brighter and larger. In your half-asleep state, it may not seem unusual, so you go back to sleep, unaware that what you are looking at is actually Mercury. The surface of Mercury, the planet closest to the Sun, looks very similar to the Moon's. It is also covered with meteorite craters. Mercury is about 2/5 the size of Earth, but slightly larger than the Moon. Because of this, the planet's influence on Earth would be stronger. Nights would become brighter, and tides would intensify. The lunar cycle, or rather Mercury's cycle, would shorten by about 14 hours. However, overall, such a replacement would not dramatically change life on Earth. But what if Venus, the third brightest object in the sky after the Sun and Moon, took the Moon's place? Venus is often called Earth's sister planet because their masses and diameters are nearly the same. In our sky, Venus would appear as large as Earth as seen from the Moon by Apollo astronauts. The morning star would shine far brighter than the Moon. First, because it reflects 6 times more sunlight, and second, because it would occupy at least 16 times more space in the sky. Nights would become almost as bright as early twilight. If you looked at Venus, you would see blurred vortex patterns in its yellowish-white cloud cover. But Venus could not become Earth's satellite. Most likely, the two planets would orbit a shared center of mass along a very unusual trajectory. If Venus moved at the Moon's current orbital speed, it would collide with Earth in the near future. Now let's consider Mars. If it took the Moon's place, you would notice immediately. Its reddish disk and size, twice that of the Moon, would be impossible to miss. You wouldn't even need a telescope to see the dark regions on its surface, and even if the unusual nighttime color didn't bother you, the consequences would. Mars is about half the size of Earth, but much more massive than the Moon. Replacing a small satellite with a larger one would severely disrupt Earth's delicate balance. Anyone near the ocean at the moment of such a replacement would have to evacuate immediately. Immense tidal waves, similar to giant tsunamis, would crash onto the shores. Mars would reflect more sunlight, making nights brighter and giving landscapes an eerie red tint. On the other hand, you could observe Olympus Mons, the tallest mountain in the solar system, through a telescope. Mars does not have enough mass to drastically alter Earth's orbit, but over time the two planets might begin orbiting a shared center of mass, forming a double-planet system. In that case, traveling to Mars would become far more feasible. Now let's imagine an even bigger replacement. If Jupiter took the Moon's place, Earth would no longer exist as an independent planet. It would become a satellite of the largest gas giant in the solar system. Although this sounds terrifying, the view would be astonishing. The sky would become breathtaking. Jupiter, vastly larger than the Moon, would dominate the entire horizon. You would see massive atmospheric bands, yellow, brown, red, and white. But you wouldn't have long to admire them. Jupiter's immense gravity would trigger devastating earthquakes, volcanic eruptions, and tsunamis. Earth's crust and mantle would begin to stretch and compress, and eventually the planet would be torn apart. Earth's orbital speed is only about 10% of what would be required to remain in orbit around Jupiter. Therefore, within less than a day, our planet would inevitably collide with the gas giant. Let's move to a more pleasant scenario. If Saturn replaced the Moon, the sight would be truly spectacular. Saturn is more than 35 times larger than our satellite. A golden sphere would fill about 18 degrees of the sky, and its famous rings would stretch from horizon to horizon. Earth would orbit slightly farther than Saturn's moon Dione. However, due to the gas giant's enormous mass, our planet would quickly become its satellite. Earth's orbital velocity would not be sufficient to avoid a collision, which would occur after a few days. On the way towards Saturn's atmosphere, Earth would have to pass through its rings, composed of ice, comet fragments, asteroids, and shattered moons. This journey would be extremely hazardous. Additionally, Earth would need to dodge Saturn's 53 known moons. And if a collision were avoided and Earth became the 54th moon, Saturn's gravity would trigger immense tectonic shifts. The crust would begin to tear apart, and eventually the planet would be destroyed, another unfortunate outcome. Next, let's consider Uranus and Neptune, the ice giants. They are nearly the same size, larger than Earth but smaller than Saturn and Jupiter. Both are covered in ice and display a beautiful greenish-grey hue. If either one replaced the moon, the consequences would be similar. Let's choose Neptune as an example. Neptune is 14 times larger than the moon. It would look like a giant, bright blue balloon, visible both day and night. It might even appear 15 times larger than the Sun, causing frequent solar eclipses. Each time Neptune passed in front of the Sun, Earth would descend into total darkness for more than an hour and a half. Neptune's mass exceeds Earth's by a factor of 17, and its gravitational pull is far stronger. As a result, Earth would once again become a satellite at a distance slightly greater than that of Triton, Neptune's largest moon. This would also introduce the risk of Earth eventually colliding with Triton. But even if such a collision were avoided, the problems would be substantial. Tides would become 1,000 times stronger than those caused by the moon. Neptune's gravity wouldn't tear Earth apart, but it would significantly heat the planet's interior. Seismic activity would gradually intensify, triggering earthquakes and volcanic eruptions. It is highly likely that technological systems, including the internet, would cease to function. Now imagine two parallel horizontal lines. Connect them in two ways, with a vertical line and with a diagonal one. Which is shorter? Naturally, the vertical line, it's the shortest path from the lower line to the upper one. The same principle applies to spacecraft. The most direct and fastest route to orbit is a straight trajectory. In this analogy, the lower line represents Earth's surface. Our planet is a complex mixture of various substances with a total mass of about 6 sextillion tons, 6,000 billion billions, an enormous number. All this mass acts like a giant magnet, which also enables Earth to retain its atmosphere. The upper line is the boundary of the atmosphere. Everything above it is orbit and open space. But the atmosphere itself is matter gas with density. When a spacecraft is launched, this layer of gas constantly exerts pressure on it, creating friction and slowing the ascent. Traveling through a vacuum is similar to cutting through air, whereas passing through the atmosphere is more like trying to force your way through a thick, jelly-like layer. Overcoming it requires enormous amounts of energy and force while facing significant resistance. Earth behaves like a massive gravitational magnet, and the pull of this force constantly affects anything that tries to rise into the air. Airplanes, unlike spacecraft, are not hindered by the atmosphere in fact. They use its density to lift off the ground and maintain altitude. This is possible thanks to two key elements: engine thrust and the unique shape of the wings. An airplane's wings divide airflow into two streams. These streams meet again behind the wing, but the wing's shape forces the upper stream to move faster. The faster the air moves, the lower its density becomes. As a result, the air beneath the wing is denser than the air above it, creating lift, which allows the aircraft to essentially glide through the air. None of this would work without thrust pushing the airplane forward. To leave the ground, it must reach a high speed, which depends on the aircraft type, about 96.5 km/h for light aircraft and roughly 241 km/h for a large airliner. Even to climb to just 3 kilometers, a Boeing 747 requires around 3 tons of fuel. These numbers are impressive, but they pale in comparison to a space shuttle. The first thing you notice about the shuttle is its small, stubby wings. They are completely useless for horizontal takeoff. Large, heavy wings would be equally useless in the vacuum of space and too fragile to survive launch stress. That is why the shuttle's wings serve a single purpose: ensuring a safe landing after re-entering the atmosphere. They are just large enough to prevent uncontrolled spinning and to guide the shuttle steadily to the ground. The engines are not used during landing. Airplane engines rely on atmospheric oxygen, but rockets operate differently. There is no air in space, so shuttles are equipped with rocket engines. Their basic principle is easy to understand using a simple balloon. Let it go, and it flies in the direction opposite to the escaping air. A rocket engine must generate enormous thrust and burn vast amounts of fuel. In fact, the shuttle needs so much fuel that 3 engines alone are not enough. For that reason, it is equipped with 2 additional solid fuel boosters and a massive external fuel tank that is jettisoned during the final stage of ascent. To reach orbit, the shuttle requires tremendous power. The combination of its 3 engines and 2 boosters produces about 3.5 million kilograms of thrust only. Then can it overcome Earth's gravity and atmospheric resistance? To generate such immense thrust, the shuttle's external fuel tank contains about 725,000 kilograms of rocket fuel. And to control the ascent, its 3 main engines must have an extraordinarily complex design. But could we launch the shuttle into orbit if we redesigned it to use the atmosphere the way airplanes do? Unfortunately, no. Flying along a long diagonal trajectory would require even more fuel, and the benefit would be minimal. Even if an aircraft could reach the upper layers of the atmosphere, Earth's gravity would still hold on to it. To leave the atmosphere, any object launched from the planet's surface must accelerate to what is known as escape velocity, the speed needed to overcome Earth's gravitational pull. Orbital velocity is about 28,000 kilometers per hour. This is far above the speed of sound and dozens of times higher than the cruising speed of commercial aircraft. Imagine an airplane capable of flying that fast. How much fuel would it need? How strong would it have to be not to fall apart? The cost and complexity of such technology would be completely unrealistic. Realizing the limitations of the shuttle led scientists and engineers to search for new, more efficient methods of reaching orbit. One such idea is the construction of a giant space elevator. A space elevator is a concept of an enormous tower extending all the way to a satellite in geostationary orbit, moving in sync with Earth's rotation. The height of such a structure would have to be about 35,400 kilometers. The proposed material for it was ultra-strong carbon nanotubes. Inside the elevator, platforms would be driven by electromagnetic systems. The trip from Earth to the orbital station would take only about 5 hours. Such a megastructure would allow people to reach space faster, more safely, and more economically. However, in practice, carbon nanotubes have proven insufficiently strong for a structure of this magnitude. The search for a suitable material continues. Another project based on a similar idea is the space tram. It involves a vertical vacuum tunnel through which a shuttle would travel using magnetic levitation. With no air to slow it down and electromagnetic pulses providing acceleration, the shuttle could be propelled to nearly escape velocity. Such a shuttle could also be lighter, as it wouldn't need to carry enormous amounts of fuel. But one problem remains: how would humans survive such extreme acceleration? At those forces, the crew would likely end up in a condition that is, to put it mildly, far from comfortable. If these ideas seem strange, and they truly do sound like science fiction, the next one may surprise you even more. In the future, airplanes might actually play a role in reaching orbit. No, an airplane itself cannot travel into space, but it can serve as a launch platform. The concept involves creating a specialized aircraft with a wingspan of about 122 meters, capable of climbing to an altitude of over 10 kilometers. A small shuttle launched from such an air platform would not have to push through the densest layers of the atmosphere. It would find it much easier to overcome Earth's gravity. Richard Branson is already working on a similar concept within the Virgin Galactic program, aiming to make suborbital flights accessible to tourists and bring humanity closer to the edge of space.